When we sketch a graph by a regular equation, y equals 3x, we have information about two variables, y and x. And it's sometimes useful to have information about a third variable at the same time. And often this third variable is time, but it does not necessarily have to be. Okay. Oops. Okay. So we're going to look at dealing with what parametric equations are. We're going to sketch graphs using parametric equations. We're going to convert between parametric equations and rectangular equations, or the plain old equations that we're used to seeing. And then we're going to take a graph and find what the parametric equations are that match it. So up till now, we've been using x and y, okay, and to represent a curve. Y equals 2x, and we might, or let's say y equals x squared. Okay, so we might have a graph that looks like this. Okay, that would be y equals x squared. Well, at any given point on this graph, we have information about the y value and the x value. Okay, and that's great, but sometimes we want more. Okay. Sometimes we want more than just where the object, if this is an object following this curve, we want to know more than just where it is. We might not want to know when it's there. Okay, so in addition to having the y coordinate, how high it is, the x coordinate, how far out it is. Let's say it's a baseball. You hit a baseball, and it follows that path. Okay, at time equals 0, you're at x equals 0. And y equals 0, right? It hasn't traveled. Okay, but as it goes up this curve, at this point, you might have, x equals 20. That's how far to the right it went, and y equals 10. That's how high it is. But what's also important sometimes is, well, when did this occur? At what point did it reach 10 feet high? Well, we'd want to know what time is equal to. Okay, so what we're going to do is we're going to define a third variable that we're going to use in these equations, and that variable will represent the unknown, or the additional desired quantity. And that variable is called a parameter. It does not have to be time, but it often is. Okay, so what we're going to do is define parametric equations. Okay, we're going to take each of our variables, and instead of defining y in terms of x, like y equals x squared, we're going to set up two equations, and each of them, okay, the x variable is going to be defined in terms of our parameter, and the y variable is going to be defined in terms of that same parameter. Okay, these two equations are known as parametric equations. Okay? And if you look at this, you could realize that, okay, if I want to start at time equals 0, what are my positions, x and y? Well, at 0, x is going to be 0. And at t equals 0, if I plug that in here, negative 16 times 0 plus 24 times 0 is 0, so y equals 0. So at t equals 0, there is the values of the x and y coordinates, so we could plot that. Okay, we could then move to t equals 1 and figure out what these values are. All right, so at t equals 1, we're going to have x equals 24 times the square root of 2 times 1 is 24 times the square root of 2. And at t equals 1, the y parameter is going to be negative 16 plus 24 times the square root of 2. All right, so negative 16 plus 24 square root of 2. And I can't simplify that because the 24 is multiplied by the square root of 2. So I just can't subtract the 16 directly. Okay. Okay. Now, the result of this motion problem, this graphing of the parametric equations, results in what's called a plane curve, and all that is just a curve. If our original equation was y equals x squared, and we converted it to parametric form, the curve would still look like the curve of y equals x squared. Okay? This is just saying that if you are graphing parametric equations and the parametric equations are smooth continuous functions, that the graphing, the solution, the plane curve, will be a smooth continuous function. Furthermore, there's kind of a direction to this because let's say I have a graph and I have parameters defined, and at t equals 0, I'm at this point. And then at t equals 1, I'm at this point. And at t equals 2, I'm at this point. So if I draw this curve, okay, and let's just say it continues on, well, I know which direction. As time is increasing, I am moving in this direction, okay, and that matters. Okay, this is known as the orientation of the curve, the way that you are moving with time. Okay, so we're asked to sketch a curve. Okay, here are the parameters, and with the curve is only defined between t equals -2 and +3. Okay, so what we're going to do is we're going to create a table of values. All right, so we're going to have our t values, of course, and then for each t, we're going to have an x value and a y value. So t goes from -2 to 3, so I'm just going to create a table with those values. And now our x is determined by this equation, t squared minus 4. Well, -2 squared is 4, minus 4 is 0. Okay? -1 squared is 1, minus 4, -3. 0 minus 4 is -4. 1 minus 4, -3. 2 squared minus 4 is 0, and 3 squared minus 4 comes out to be 5. Okay, let's do the same thing for y. Y is defined by t divided by 2. So t is -2 divided by 2 is -1. -1 half, 0, 1 half, 1, and 3 halves. Okay, so if we come over to our graph, we're going to plot the x and y points. Okay, the first one is 0, -1. Right there. That's our first point. Our next one is -3, -1/2. So -3, -1/2. Okay. -4, 0. -3, 1/2. 0, 1. And 5, 3 halves. Okay, so if I connect these dots, I go this way, kind of, make that a smooth curve, of course, and we are going in this direction with time. So I'm going to put these little arrows on here, and it stops here, and it starts here. Okay, and that's because we are in this interval. Okay, so that's what my graph of the parametric curve would look like. Okay, that is a plane curve. It's got an orientation that is moving around this direction. Okay, it is possible, and it often happens, that two parametric equations or two sets of parametric equations have the same graph, or at least it looks like the same graph. Okay, and despite their color, these are the same graph. The difference is that if you look at t, okay, this does this entire curve between -2 and 3. That's the one we just graphed. So that's a total of 5 seconds if the unit of time is seconds. Okay. This does the same curve, okay, the same plane curve, but it does it between -1 and 3 halves, and that is 5 halves seconds. So it does the same thing, it just does it in half the time. So while the curves look the same, there is a difference. Okay, since plotting points can be tedious, we're going to do something called eliminating a parameter. And elimination of the parameter is going to allow us to convert a set of parametric equations into a rectangular equation that we know better how to graph. Okay, so this is kind of the process here. We'll start off with a set of parametric equations. We're going to solve for t in one of the equations. Basically, all we're doing is a substitution. Okay, so we're going to take that value of t, and okay, we solved this second equation, okay, if we solve, oops, if we solve this equation for t, we get t equals 2y. Then we're going to take that and plug 2y into our other equation for t. Okay, that's what this is, 2y quantity squared minus 4, and then solve it. Okay, so our rectangular equation turns into x equals 4y squared minus 4. I know we're used to seeing y equals maybe 4x squared minus 4, and really what happens is this is still the graph of a parabola, except it's a parabola on its side, which in essence is not a function because it fails the vertical line test. Okay, we have two intersection points. Okay, but that's okay. Parametric equations do not have to represent functions. It gives you that flexibility. So we're going to go ahead and eliminate the parameter here, and we're going to then look at the graph and figure out what the restriction on the domain is, because we have to take into account the domain. Okay, so we're going to solve one of the equations. I'm going to pick x. I'm going to solve that for our variable t, and the way I'm going to start is by squaring both sides. So I'm going to wind up with x squared equals, okay, 1 over the square root of t plus 1 quantity squared. And when I square a fraction, all I need to do is square the numerator, 1 squared is 1, and square the denominator, which is just going to be t plus 1. So x squared equals 1 over t plus 1. What I'm going to do is write that, and I'm going to go ahead and cross multiply, and that gives me x squared times t plus 1 equals 1. Okay, let's distribute. X squared t plus x squared equals 1. And now I'm going to go ahead and solve for t. So I'm going to subtract this x squared off. So I get x squared t equals 1 minus x squared, or t dividing by x squared on both sides now. 1 minus x squared, all divided by x squared. Okay, so now we've solved for our parameter. And what we need to now do, draw a line down here. Okay, that's solving for the parameter. Now what we're going to do is substitute. And of course we used x equation to solve for the parameter, so we're going to substitute into the other equation, into y. Okay, so this becomes y equals, everywhere where I see a t, I'm going to put in this value, 1 minus x squared divided by x squared. So it's going to be a compound fraction, 1 minus x squared divided by x squared, all divided by 1 minus x squared divided by x squared plus 1. Okay. So now I need to simplify this compound fraction, and what I'm going to do is I'm going to multiply by the denominators, which is just x squared. Okay, the reason I'm doing that is that these will cancel out, and that gives me 1 minus x squared in the numerator, and in the denominator I have to distribute. Okay, this is going to give me 1 minus x squared, that's x squared times this first term, and then plus 1 times x squared is just x squared. Well, these cancel, so they're opposites, and I get y equals 1 minus x squared over 1, which is really just 1 minus x squared. Alright, and if we want to, we can write this as y equals negative x squared plus 1, which is kind of the format we're more familiar with. If I were to go ahead and graph that, I would get a curve. I've got an intercept of positive 1, and it opens down because of the negative x squared, so it's going to look kind of like this. Okay, but we're not quite done yet because we need to pay attention to the domain. Okay, right now it looks like x can take on any value.